tell us more about light gray operators?
So I want to first thank the organizer for putting together this wonderful conference, giving me this opportunity to speak. I used to be a student here, so it's a great pleasure to be back here to you. Uh, Today I want to talk about an ongoing project with Hao Chen, Peter Krabshaw, Davidson, and Stuffin in Washington. So as Ian mentioned in his talk, it's very interesting to study these kind of detector operators. And the motivation for this work is to explore what kind of other detector operators exist in QCD. And so we've seen this very special kind of detector, which is the ANAC operator that measures the flux of energy in infinity. And Ian just gave a beautiful talk about how to connect the theoretical understanding of that with some real-world collider data. Kai also mentioned how to compute these, also explained how to compute these energy correlators to very high precision. That's great. But so given all these results about energy correlator, I think it's natural to ask what else can we measure at infinity? Sometimes you're kind of forced to ask this question because when you have more than one ANAC operator, and you take the OP between them, the dominant contribution is some more general detector. It's something that doesn't measure energy, and it measures something else. But we have to understand that. And so the target would be QCD, but it's very helpful to think in terms of conformal field theory in CFT. So in the CFT, detectors can be identified with what's called the Lyra operators. So our strategy will be starting with the free theory, and we'll construct these detector operators using Lyra operators. And then we ask what happens when we turn on interactions. And when you do that, for these special detector like ANAC, it remains IR safe. But for general detectors, you'll get divergences, or you'll get infrared divergences. So that means we'll have to understand how to normalize these detectors and get a good observability. And furthermore, sometimes these detectors can mix with each other in a very non-trivial way. So I'll try to explain how that can happen in QCD. And just to be clear, I think we're still kind of at the early stage of exploring these general detectors. So of course, it will be very interesting to study correlations of these general detectors, but today I'll mostly just talk about one-point function of them and understand how to normalize them. Also, everything I say today will be leading order. So the detectors I'm going to talk about will be related to two very important equations in QCD. They're in the title of my talk, DGLAP and BFKL. So just to review several basic facts, the DGLAP equation, it controls the evolution of PDFs under RT flow. And there's an important quantity that enters the equation, which is the anomalous dimension of twist two local operators. So this is one of the entry of that anomalous dimension matrix. It has this expression. And on the other hand, there's also the BFKL equation. It controls the scattering at very high energy, so-called Regge limit. So essentially, it resums all the large logs of S over minus T. There's also an important quantity that I'll call the BFKL eigenvalues or anomalous spin. It depends on some variable nu, and it has this expression. These two equations they're not independent. They can mix with each other. So the DGLAP equation breaks down as small x, but then these large log can be resummed using BFKL. Another way of understanding this is by looking at these anomalous dimension of twist two operator. You can take that expression and try to go to j equals to 1. There's no local operator there, but you can just we continue it to j equals to 1. And when you do that, you'll find that there's a pole. And this just means taking j goes to 1 does not commute with weak coupling expansion, so you have to perform a resummation. And when you do that, you'll see it's actually not proportional to alpha s, it's proportional to square root of alpha s. Similarly, the BFKL eigenvalue also has a pole at this variable nu equals to -2. You'll notice they have exactly the same residue. These pole and this is not a coincidence. This is because these poles are related to some non-trivial mixing between these two equations, DGLAP and BFKL, and so they satisfy some very non-trivial relation. Actually, this is even true in higher order derivative theory. So there are lots of exploration of this in both QCD and AQST. So let me just. So these are well-known facts, but today I'll try to understand these facts in the language of library operator and detector. So basically, I'll construct detector for DGLAP, I'll construct a detector for BFKL, and I'll show that if we work in an appropriate basis, we can kind of resolve this mixing problem and get a finite anomalous dimension matrix even when they mix. So, so I guess I got an assignment from Ian to explain what library operators are, but actually I'm not gonna write down what they are. And I'll write down some special examples, but for now, let me just say some properties about them. So there are things you can define in the non-perturbative CFT, and they analytically continue some integral transforms of local operators. And these integral transforms are called the light transform. These light transforms depend on a space-time point x and a null direction z. So this z is a null vector. So what this integral does is just you start at this point x and then you integrate it along this null direction z. Okay. And this integral changes the quantum number in this interesting way. So this delta L and JL is the scaling dimension and spin after doing this integral transform. This talk, I'm always gonna put this x as spatial infinity, and when you do that, this null integral becomes an integral along future null infinity. So you can look at this Penrose diagram. This entire circle is just a point, it's spatial infinity. So you start here and then start integrating it along this y plus. You would have some null direction z, which is in fact the embedding space coordinate selection sphere. So it's a point on the selection sphere. And I'll call this thing the detector operator. It's some continuous spin JL, and it's on null direction z. And if you recall, the definition of ANAC is really just this thing where the operator you're integrating is this resting sphere. And given a detector, you can always construct what's called a spin shadow of that detector. And the spin shadow is another integral over the celestial sphere. So, so this is some appropriate measure for the celestial sphere. And so you take that, you take your detector, and then you smear it over the entire celestial sphere in some particular way. And it will change the Lorentz spin JL in this way. You take JL to 2 minus T minus J. Okay, so I want to explore the space of these detector operators. And to me, I think the best way of showing the space of detector is by drawing what's called the true Fauci plot. And this plot is going to show up many times in this talk, so let me try my best to explain it. So what you do is you first take all your local operator of your theory, and then you plot your local operator on this plot according to their spin and their scaling dimension. When you do that, you'll find that you can connect them with some continuous trajectory. These are called Regge trajectories. For example, this red line goes through all the twist 2 operator. This blue line goes through all the twist 4 operators. What this trajectory gives you is a continuous family of detectors. So at the geometric point on this line, you have a detector operator. And, I'll call this red trajectory the DGLAP trajectory. And remember that for each detector, we can construct a spin shadow of it. So you also have the spin shadow on this plot is just a flip like this. So you also have this shadow trajectory here. And moreover, there's also some perhaps more interesting trajectory that are horizontal on this plot. So it can take any value of JL, but it has a fixed value of delta L. So I'm sorry. So now I'm going to detector. So I'm switching to this delta L and JL, actual quantum number of the detector that are related to original delta and J. Right. So these horizontal trajectory have fixed value of delta L, and this one, this leading one here, is actually the BFKL trajectory. And so this is the space of detector operator in the free theory. And if you look at this plot, you immediately notice there are a lot of intersections. So they intersect places. And I'm gonna focus on this intersection. This is where the DGLAP and BFKL trajectory intersect. They intersect at JL equals 2 minus D or minus 2 plus 2 epsilon integral. Let me zoom in during this intersection, and I want to ask, what does this plot look like when we turn on interaction? What does it look like at one loop? So first comment is that when you turn on interaction, let's say you have a detector that sits here. At zero coupling, the JL should remain unchanged because Lorentz symmetry is exact, but you will get the corrections in delta L. So the vertical position of the detector will have a small shift. And the vertical position on the true Fauci plot is originally J, so I'll sometimes call it anomalous spin. So, and actually, we already know the anomalous spin of these two trajectories. The anomalous spin of the DGLAP trajectory is related to the twist 2 anomalous dimension this way. And the anomalous spin of the BFKL trajectory is just this BFKL eigenvalue that I showed earlier. So we know their expression, and so perhaps the first thing you would do is just take this expression and then try to plot it, and you will get this blue curves. So as you can, so you see a singularity here, and as you can probably guess, this is not the correct picture. So sorry. Oh, there we go. Right. So see a single. So right. So this is the curve that you get if you take this anomalous spin and plot it on the structure plot. And so there's a singularity. Right, so there's a singularity at the intersection, and so this is not the correct picture, as you can probably guess. In general, you don't expect rigid trajectories to look like this, and we'll have to understand how to resolve this singularity by studying this non-trivial mixing between two trajectories. Now, let me also make another comment, which is these true Fauci plot can be, they are much better understood in planar equals for Young Mills because there you can use integrability. And in fact, you can make this plot at any finite coupling. And, but what was found in these papers is that any finite coupling, when there's intersection like this, they always kind of smoothly connect each other. And so you always get some smooth trajectory, or it's actually a smooth surface that just connects these two. You never see a singularity like this. So we will have to understand how to resolve this perturbation theory. So that's what the rest of my talk will be about. So I've been talking about these detector operators, but I haven't really told you what they are. Well, here's the definition in free theory. So for simplicity, I'll consider pure Young-Mills. So just gluons for now. At the end, I'll show the result, including quarks. Okay. And I'll start with the DGLAP detector. This is the definition. And what it measures is the flux of energy raised to some power. It's e to the 2 minus d minus JL, where JL is the spin. It's the Lorentz spin of the detector. So when this power is 1, you get the ANAC operator, but and you can construct it also using Lyra operator. So here's one example of general Lyra operator. You do it by integrating 2 field strings over this null line, and again some special kernel. It's like this that is chosen such that the detector has the correct Lorentz spin. So in free theory, this is well defined for any complex value of JL. But we want to know when we turn on interactions, we get all sorts of divergences, and we want to know how to normalize it. So the way you do that is just by computing some matrix element, computing the matrix element of this detector in some state created by local operators, and you want to compute it at one loop level. And so the state we are considering is this state created by the trace f squared, and so here's one example of the diagram you have to compute. There are many more. And the best way to do this calculation is also using this in-end formalism that we've seen several times. There is one difference. The difference is that when the particle goes through this detector, which is this box here, you have to replace the usual White-Mine propagator with this detector vertex. What this vertex does is, first, it localizes the momentum to null direction z, and then it has some weighted, it has some weighted with energy raised to some power. So you can go ahead and do the calculation. You'll find that it has 1 over epsilon. Probably expect proportional to the tree-level matrix element of itself, and then see this remainder in DGLAP. That's good. That means we can try to multiplicatively renormalize it by introducing some 1 epsilon in the normalization factor. But there's a problem because this gamma DGLAP has a pole at J equals -2. And from the detector perspective, this is really a problem because we do expect the detector to exist at J equals -2. And the fact that you get infinite anomalous dimension means we still have not normalized it at that value of JL. Actually, this pole at JL equals -2 is there even for finite epsilon. Right. So this pole, the pole at J equals to -2, show that even at finite epsilon, and if you look at the calculation more carefully, you'll find that it's proportional to the tree-level matrix element of a different detector. And this detector is exactly the BFKL detector. So now you see the mixing is happening like this. There's perhaps a more general argument for why this pole in JL has to appear. It really just comes from the leading software. So when you consider the limit where the particle that's being detected is soft, and then you apply the soft theorem, you will find this integral in beta. Integral in beta gives you this pole in JL equals -2, and the remaining thing has to be the tree-level matrix element. The BFKL detector. In fact, that's how we find the correct definition of the BFKL detector. So this detector is doing something funny. It has two this FABC vectors, and then there's also another vector coming from this also vector. So the correct definition of the BFKL detector that gives. Okay, so right, so this is the definition of the BFKL detector. You start by constructing what I call the color interference detector. The joint indices of A dagger and A are different, and you contract them with some FABC. Now this object has a free adjoint index C, so you can take 2 of them, and furthermore you smear it against some special kernel over the entire selection sphere. This object you construct will have some definite Lorentz spin JL, and again depends on the single null direction Z. You can also write down a Lyra operator corresponding to it. This Lyra operator also make it obvious why it's gauge invariant. It's a Wilson loop at future no infinity. So you maybe let's say you start here and then you go along Z1, and then you come back going along Z2. Furthermore, you decorate this Wilson loop with field spin. If you do the dimensional analysis, you will find for any value of JL, this object has the same value of delta L. True Fauci plot, that gives you a horizontal trajectory. So that's the definition, and then you can go ahead and compute its 1 loop matrix elements. You'll find, again, the 1 over epsilon pole is proportional to the tree-level matrix element of itself with this BFKL eigenvalue. So that's why this gives you the normal spin detector. But similar to the DGLAP case, it has another pole, JL, proportional to the tree-level matrix element, DGLAP. There's also this mixing here. So now that we've identified all the divergences of the DGLAP detector and BFKL detector, we're almost ready to try to resolve this mixing problem. But there's another fact that's also very important. This fact is that if you recall, the free theory, the DGLAP and BFKL trajectory intersect at JL equals to 2 minus D. And so at this point, you might think so at this intersection, you might think there's a degeneracy. But that's actually not quite true. What really happened is that at this point, they just become exactly the same. Two detectors are just the same thing. And this follows from some special property of this kernel we're choosing and from gauge variance. So I don't have time to show the full derivation, but eventually you get this equation. So why is this important? This means that to make sure the basis is regular at all values of JL, in particular at the intersection, you need to consider something like this. So at the intersection, the denominator is 0. But the numerator is also 0. Expect. So so that gives you some sort of new factor that's kind of still independent of the origin. And then we found that it's very important to work with this basis. So if you use this basis and just study how the dilatation generator acts on it, it will transform like a log multiplet. And then to define a renormalized detector, you just like what you would usually do for a local operator, you introduce a renormalization factor, right? But importantly, this renormalization factor has to remove not only just the 1 over epsilon divergence, you also have to remove these type of divergences. Because they show up even for finite epsilon, so you can never remove them. But this can be done, and after you do this, it's just the usual process of finding the anomalous dimension. And eventually, this is what you get. And this matrix is just a smooth function of JL. There's no divergence at JL equals to minus 2. So the eigenvalue of this matrix gives you minus tilde L, gives you the minus tilde L of the detector. Away from you can check that away from the intersection, it's consistent with the DGLAP and BFKL. But at the intersection, what you should do is that you should plug in JL equals to minus 2 here, and then a finite matrix, and then you solve for its eigenvalue. You will find that it gives you this square root of alpha s that's predicted by summation. And perhaps a better way of showing the result is just to show this true fraction plot again. So you can, the way we make this plot is just plot the eigenvalues of this matrix at JL, and you see that you get a beautiful curve interpolating between DGLAP and BFKL, and so we successfully resolve this singularity that we saw earlier on the naive plot. So that's the story for pure Young Mills. Now let's add quarks, and so now we're considering QCD. In QCD, there are 2 types of DGLAP detectors. One of them measures gluon, the other one measures quark, but actually only one of them will mix with BFKL. A special linear combination. And to see this, you can study the anomalous dimension matrix, 2 by 2 matrix, but at the intersection, only one of the eigenvalue is divergent. The other eigenvalue is finite. So turns out that it's this special linear combination of the DGLAP of the quark and gluon factor that makes this BFKL. So the coefficients are CA and CF as they're joined in 1, 2. You can repeat the same equation. Now you have 3 trajectories. You have 2 DGLAP and 1 BFKL, and the recombined trajectory will look like this. You have a trajectory that just kind of goes through the middle. This is the trajectory that does not participate in the mixing, and then you have 2 other trajectories that again mix with each other and get combined. That gives you a much bigger splitting because of this square root alpha s enhancement. So that resolves this intersection, this DGLAP intersection. But look at the free theory true fraction plot again. True fraction plot again, there are infinitely many more intersections. And ideally, when you turn out interactions, what you expect is that all these intersections will get resolved. They will kind of all recombine and form a smooth trajectory. just under the same mechanism that I just described. But today I'll just focus on these two other trajectories. Okay. This dot is really just the spin shadow of the one that we just considered, so it's really trivial. But this dot is kind of it's due to, you can use self-leading self theorem to show that it's due to a mixing between DGLAP and its spin shadow. So you have to include these also, these two trajectories. And but the same method still works. And at the end, you can include all these 5 trajectories. So there are 2 DGLAPs here, and then 2 shadow DGLAPs here, and then 1 BFKL over here. You just go through the calculation, and at the end you will find a 5 by 5 dilatation matrix that is finite near all the intersections. It has some pretty interesting. Oh, sorry, it's not. Okay. Right. So here's the plot. This is the true Fauci plot, or equivalently the spectrum of detector operators in QCD at once for at least part of it. And this is the DGLAP and BFKL intersection that I mentioned earlier. This is the new intersection coming from DGLAP mixing with its shadow. The shape of it has some interesting dependence. You can understand it by looking at how the DGLAP anomalous dimension diverge at this point. So if we plot the naive DGLAP anomalous dimension, it would diverge at this point, but the way they diverge is different. These two different values of the set, that kind of determines the combined trajectory. Okay, so let me now try to summarize in directions. So we've discussed 2 types of detector operators in QCD, DGLAP and BFKL. And we found that they mix in a very non-trivial way, and then to understand that mixing, you have to introduce some sort of new type of subtraction in your normalization. But at the end, you can find a finite anomalous dimension matrix to give you the smooth Reggie trajectories on the true Fauci plot. So there are several kind of obvious generalizations, like go to higher order, and sure in that case we can borrow techniques from the Influence community, and you can introduce more intersection, or you can look at some other sectors like odd-spin. There seems to be some interesting connection between divergence of these DGLAP anomalous spin and self theorem. So divergence at j equals 1 corresponds to leading self theorem. Divergence at j equals to 0 corresponds to sub-leading self theorem. So you can ask, is the divergence at j equals to -1 correspond to any sort of sub-leading self theorem? We also determine the shape of the recombined trajectory at j equals to 0, and just like the trajectory at j equals to 1 gives you the leading behavior in the Reggie limit, the trajectory at j equals 0 gives you the sub-leading power term. So you'll be interested to figure that out. There are also many other approaches to BFKL physics using like anomalous lines. So we should try to understand how our BFKL detector can fit in. Another very important question to ask is what is the OP between these general detectors? So we've understood the OP between ANAC operator, that's the library OP, and then, but there are infinitely many more general detectors. The ANAC operator is a point on this trajectory, and the OP between these general detectors is still unknown. You can also ask the same question about detector operators in gravity. There's a paper yesterday, and Ian also talked about it like 30 minutes ago. Finally, in the real-world collider, we don't have quark or gluon detectors, we have hadron detectors. So we should try to understand, is there any kind of metric relations between hadron detectors and the quark and gluon detectors that we're studying? And thank you. That's all.
Any questions?
Okay, well, maybe we can take the discussion over coffee then. Oh,
No question. Yeah, just to quickly describe. So coffee is going to be now, but we'd like to start roughly on time, unfortunately, because, well, because we're expecting additional guests for the next talk. So, so the coffee break will be 20 minutes instead of 30.